In this module, we're looking at new types of behavior. So we're going to need some slightly new forms of notation. We want to talk about those. We want to introduce a new theorem that's going to help us evaluate some of these problems. So we know that a vertical asymptote exists whenever we try to evaluate any of these limit problems. So if we try to evaluate the limit as x approaches a of some function, as we try to evaluate the limit as x approaches a from the right-hand side, or we try to evaluate the limit as x approaches a from the left-hand side of f of x. So we can be evaluating any of those three limit problems individually. As soon as we get either positive infinity or negative infinity as an answer, we know that we have a vertical asymptote. So as a note, something just to be aware of, if we get positive infinity or negative infinity as an answer for one of our limit problems, that actually means that the limit does not exist. We'll still write that that limit equals infinity or equals negative infinity because that gives us some more specific information about the way that the limit doesn't exist. But if we have a vertical asymptote, technically the limit never exists. We know that a horizontal asymptote exists if we try to evaluate the limit as x approaches infinity. So now this is slightly different notation. Previously, x has always been approaching some individual value. So now the limit as x approaches infinity, just getting larger and larger and larger of our function, or the limit as x approaches negative infinity of f of x. If we're evaluating either of those two problems and we don't get infinity or negative infinity, then we know that we have a horizontal asymptote. So if we're evaluating this limit or this limit and we get a real number as a result, then there is a horizontal asymptote. If we evaluate either of those two limit problems, the limit as x goes to infinity of f of x, or the limit as x approaches negative infinity of f of x, and we do get infinity or negative infinity, then we know that our graph at the ends diverges to either plus or minus infinity, whichever end that we're talking about. Or another way of saying that is there is no horizontal asymptote. So to get a vertical asymptote, we only have to look at one of these three limit problems. When we're talking about the end behavior of a graph, we're always going to evaluate the limit as x goes to infinity and negative infinity. So there are always going to be two separate problems to evaluate when we're thinking about end behavior. So we have a new theorem that we want to introduce, which again is going to help us evaluate some of these problems. In these cases, we're assuming that p is a positive real number. And k is some constant besides 0. So in our first part of the theorem here, we have the limit as x goes to negative infinity of k over x raised to some power. So this would be like 1 over x squared, or 15 over x to the 27th power, something like that. A limit problem like that is always going to equal 0. The reason being, if we consider one of those examples, we take the limit as x approaches negative infinity of 1 over x squared. We can just plug in larger and larger values for x. So we could start with 1 over negative 10 squared, 1 over negative 1,000 squared, 1 over negative 1 with a whole bunch of zeros after it. And you could plug those into your calculator, evaluate those, see that as this number in the denominator keeps getting larger and larger and larger, we're getting closer and closer and closer to a value of 0. And the same thing is going to be true if we have some constant divided by this power function, x raised to some power, and x is approaching infinity. Through a similar logic steps, we could arrive at the same result. We could look at 1 over 10 squared, 1 over 1,000 squared, 1 over some really huge number squared. That pattern is going to keep getting closer and closer and closer to 0. If we consider the limit as x approaches negative infinity, in this case, of a constant times this power function, x to the p power, this is either going to be headed to positive or negative infinity in every case. So we have two different possible solutions here, and that's going to be dependent on whether p is odd or even, and whether k is negative or positive. So x is headed to negative infinity, and we're taking x and raising it to some power. If we raise it to an even power, that's always going to end up giving us a positive result. If it's raised to an odd power, that's always going to give us a negative result. So we have the possibility to have positive or negative results there. And then whether k is positive or negative, then we either end up with a positive times a positive, negative times a negative, negative times a positive. We have a few different scenarios that can happen there. So we need to consider what the sign of that constant is and what power we're raising x to, if it's to an even power or an odd power. If x is approaching positive infinity, then we have that same expression. This can still head to either positive or negative infinity. But in this case, it only depends on whether k is positive or negative. So we're plugging in positive values into x and raising it to some power, so that x to the p part is getting larger and larger and larger, and then we're multiplying it by some number. If we're multiplying it by a positive, we're just getting a bigger positive value. If we're multiplying it by a negative, then whatever this x to the p is getting multiplied by a negative, so our result is negative. So we always have to consider what that coefficient is whenever x is heading to infinity.